I hope my screen is visible to everybody. Yes, students,
Yes,
is it
sure.
visible
Yes,
correctly?
sir. Yes,
Okay.
sir.
So let us start. So in the previous class, if you remember, we have gone for the derivation of the stiffness matrix for the simple bar element. Okay. And if you remember, we have gone for k equals to AE divided by L, 1 minus 1 minus 1 and 1 will be the stiffness matrix for 1D bar element. Okay. So today we are going to cover a few problems for 1D bar element. So I want everybody to have a calculator with them because today you have to do a lot of calculations. Okay. So let us quickly start with the very first problem. So we are starting with a very basic and very simple problem today. So what I'm going to do is let me create a simple uh, bar over here. So let us say this is my simple bar. Okay. And let us say that here we have a fixed trend. Okay. And just imagine that at this point, okay, we have a concentrated load, let us say 1000, 1000, let us say Newton is acting over here. Okay. So let us say this is 1000 Newton over here. And let us take the say the length. Okay. So here, let me take the length. Okay. So I'm intentionally taking the values. Okay. So let us say the length is, let us say 500 millimeters. Okay. So now we need to analyze this particular problem using the finite element method. Okay. So let us start. So let us with the solution. Okay. Now if you remember, in the finite element method, the entire solution process can be divided into say six number of steps. Okay. So step one is called as discretization. Okay. Discretization. Okay. So this discretization means what? We have to break a given problem into n number of elements, right? So now fortunately our problem is very simple. So what we can do is we can have in the step one a very simple discretization of the structure. So let us say I have a simple bar kind of a structure. Okay. So I am just using only one element. Okay. So let us call this is element number one. Okay. And let us say that it has got node number one, which is over here, and node number two, which is over here. Okay, a very simple basic one. Okay. And since we have only one element, we will be using the global coordinate system. Okay. So let me use a global coordinate system. So this is your global coordinate system. So this will be something like your x, and here your x value will be 0. Okay. So let us call this as x1 because this is node number 1, and this is called as x2. So this is node number 2. So this is 500 millimeters. Okay. So this is how I am discretizing the problem. So there is only one element, and there are only two nodes. Okay. Now in the step 2. Okay. So can anybody tell me what is the step 2? Anybody? क्या था step 2 finite element method में? Yes, anybody remember? Okay. याद है कुछ? So it is called as elemental characteristics. Okay. Elemental characteristics, right? So we are using a simple bar element. Okay. So we have already calculated the elemental characteristics. So this elemental characteristics means what? It is nothing but a derivation of your stiffness matrix for that particular element. Okay. So we have already derived this, so we are directly going to use this. Okay. So in the problem, if it is mentioned that you have to derive the stiffness matrix also, then you have to go for the derivation first and then we have to solve the problem. Okay, but as far as this problem is concerned, we don't have to derive any elemental stiffness matrix because we have already calculated the elemental stiffness matrix. Okay, so let me write down the elemental stiffness matrix over here. So K, let me call this as K elemental. Okay, so this is nothing but A E upon L, and we have 1, -1, -1 and 1. Okay, so while defining or while deriving this elemental stiffness matrix, so let me refer the notes of the earlier class. So what we have assumed, okay, so we have assumed the area. So from this point to this point, we have assumed the area as constant, as well as the modulus of elasticity E is also constant. This is what we have assumed while while deriving the expression for the stiffness matrix. Okay, so if you see this problem, so in this problem the area is constant and the area is also sorry, the modulus of elasticity is also constant. Okay, I forgot to mention what is the area over here. So let us assume the value of area as constant. So let us say this is 1000 millimeter square, and the modulus of elasticity of the material of the bar is, let us say, 200 gigapascal. Okay, so this is what I am assuming. Okay, so the area is constant, modulus of elasticity is also constant, so this is exactly matching with what we have assumed for the derivation of the stiffness matrix, and the derivation of the stiffness matrix comes out to be something like this. Okay, now in the step 3, what we have to do, can anybody tell me what is the step 3? Okay, in step 3 we have to go for stiffness matrix. Okay, so let me calculate the stiffness matrix. So your stiffness matrix, since there is only one element, we have to calculate only one stiffness matrix. Okay, so I am just going for K1. Okay, so this 1 stands for element number 1. So remember, we are using only one element over here. So here, so I'll be writing over here, so this will be area of element number 1, modulus of elasticity of element number 1, divided by length of element number 1, multiplied by 1, -1, -1 and 1. Okay, so now let me substitute the values over here. So let us keep everything just to have a common platform of units. So let us keep the load values. Okay, so let us keep the load values in newtons. Okay, and the distance values in, let us say, meters. Okay, so these are the basic things, right? So if you go for area as 1000 millimeter square, and if you go for the conversion of millimeter square into meter square, so can someone tell me how much it will be? 1000 millimeter square to how much is meter square? Yes, anybody? Bolo?
So 1 into 10 to the power minus 3.
Yes, 1 into 10 to the power minus 3. This will be meter to the power 2. Okay. Now, this 200 gigapascal. So, this is 200. So, one is kilo, mega and giga. So, this means into 10 to the power 9. Pascal means what? Pascal is newtons per meter square. Okay, so you can see now everything is in meters and the forces are in newtons. Okay, so I'm just substituting the same values over here. So this is 1 into 10 to the power minus 3. So this is 1 into 10 raised to power minus 3 into 200 gigapascal. So this is 200, okay, into 10 raised to power 9, okay, divided by the length of the first element, and it should be in meters. Okay, so length of the first element is 500 millimeters. So 500 millimeters will be nothing but 0.5 meters. So if you multiply this, so this will be 1, this will be -1, -1 and 1. So can someone tell me how much is the constant value over here? Yes, somebody please tell me the values. Yes, how much is this?
400 into 10 to the power 6.
400 into 10 to the power 6, okay, into this is 1 minus 1 minus 1 and 1, okay. So this is the stiffness matrix for the uh, single element, okay. Now the next step is to assemble the global stiffness matrix, okay. So this is step 4 is stiffness matrix, okay. So here we have only one element, okay. So as such the global stiffness matrix will be exactly same as the local stiffness matrix at k1. So your k global will be same as 400, okay, into 10 to the power 6, okay. This will be 1 minus 1 minus 1 and 1. So this is your step number 6, okay. At the same time you have to write the global force vector also. So this global force vector is nothing but your force vector in which the forces are acting in the direction of the global axis, okay. So this is the force vector, okay. So this is I should write it in curly brackets because this is a vector, okay. So this global force vector will be the force at node number 1 and the force at node number 2 in the direction of the global axis, okay. So if you refer this particular problem, this is your node number 1 and at node number 1 there is a fixed support, there is no load, and at node number 2 there is a load of 1000 newtons, okay. And this 1000 Newton is acting in the direction of the x-axis which we have assumed. So now what is going to happen over here is like this, okay. Oh, again I'm making the same mistake, it should be a vector, okay, not the matrix. So this should be like this, so this will be 0 and this will be positive 1000, okay, because the force is acting in the direction of the global x-axis, okay. Then in the fifth step we have to solve this, okay. Solve for unknown, okay. So solve for unknown means what? Since the global matrix and global force matrix both are known, our stiffness equation, so stiffness equation is k global, okay, into you have the displacement, okay, equals to we have the force global, okay. So we have already calculated the stiffness matrix. It is consisting of a simple 2 by 2 matrix. So this is 400 into 10 to the power 6. So this is 1 minus 1 minus 1 and 1, okay. And your global force vector, sorry, global displacement vector will be the displacement at point node number 1 and displacement at node number 2, okay. And this will be equals to the force vector, so this will be 0 and this is positive 1000, okay. So now this part is done. So now we have to solve this, right? So if you refer the figure over here, displacement at node number 1 is 0 because there is a fixed support over here, isn't it? So what I can do is I can simply delete this value. So this u value is basically 0, okay. So you might have studied in the matrix method. So in matrix method, like if your u value is 0, then what you can do is you can remove the respective row, okay, and you can remove the respective column over here, isn't it? So at the end what is going to happen over here, we are going to end up with only one equation, and that equation will be 400 into 10 to the power 6 multiplied by 1, and this will be something like u2 equals to we have 1000, okay. So now you can solve this particular expression and you can get me the value of u2, okay. So can somebody please tell me what is the value of u2, please? कितना आएगा ये? Yes, somebody please tell me. Yes, students, please somebody tell me.
Sir, 2.5 into 10 to the power minus 6.
2.5
into 10 to the power minus 6.
Are you sure? हाँ बराबर है. So this is 2.5 into 10 to the power minus 6. What will be the unit? It will be in meters, okay, because everything is going on in terms of newtons and in terms of meters, okay. So this is the units which we have assumed, okay. So basically what is happening over here is the this particular point now will be subjected to a deformation of 2.5 into 10 to the power minus 6 meters, and that deformation will be there in the direction of the axis, okay. So this is step 5. I think I missed the 5 over here, and then in the step 6 we can go for the extra calculations, okay. So extra calculations, okay. Now in this extra calculations you can have n number of outputs, okay, depending on what is asked in the exam, okay, or what is asked in the numerical itself, okay. So the very first thing is you can have the variation of displacement, okay. So what is variation of displacement? It is nothing but, if you remember correctly, in the previous class we have assumed the value of u, okay, with some polynomial displacement, and then we are ending with this something like n1 and n2 equals to, we have u1 and u2. Do you remember this? Okay. So you can even refer the earlier notes also, okay. So here you can see we have calculated the value of u here, okay. So u is nothing but n1 n2 multiplied by u1 and u2, where n1 n2 they are called as the shape functions, isn't it? Now if you refer the earlier notes, your n1 value was something like 1 minus x upon L, and your n2 value is nothing but x upon L, okay. So if you rewrite this particular expression, so this is 1 minus x upon L, this will be in bracket, and this will be x upon L, this will be also in bracket, multiplied by, you have u1 and u2, okay. So now we can make use of this expression to find out the displacement at any point in the bar, okay. So for example, if I draw a bar one more time over here, okay, and if you remember, this was your node number 1, this was your node number 2, this is node number 1, this is node number 2, okay. So right now if I want to calculate what is the displacement at this particular point, okay. So this is let us say our the length of the bar is let us say 500 millimeters. So this is given over here. So let me draw a 500 mm distance over here. So this distance is basically 500 millimeters, okay. Let me put it correctly. It's not getting correctly, but anyway, so we can have over here say this is 500 millimeters, okay. And let us say I want to know what is the distance or what is the displacement at this particular point, and let us call this particular point is, let us say, 150 millimeters, okay. So let us call this point as P. So my target is to find out what is the displacement at point P. So we will call this displacement as UP, okay. Now if you want to do these calculations, so remember that in our problem we have assumed the origin over here, and this was my x-axis, okay. So all we have to do is substitute the value of x as I think I have written 1500 by mistake. It should be 150, not 1500, it should be 150 millimeters, okay. So all we have to do is substitute the value of x as 150 millimeter and length as 500 millimeter, and then you can get the values of the displacements, okay. So let me rewrite this particular expression at the bottom, okay. So your u, okay, u at point P now can be calculated as, so this is 1 minus x upon L, so this is first thing, then x upon L, this is the second shape function, and this will be multiplied with u1 and u2. Okay, so now in this expression what we have to do is this x will become now 150, this x will also become 150, and this L will become 500, this L will become 500. U1 is the deformation at node number 1, which is 0 because there is a fixed end, and U2 is the deformation at node number 2. Just now we have calculated the value of U2 as something like 2.5 into 10 to the power minus 6. Okay, so this is in meters. Okay, you have to substitute these values in meters. Even if you don't substitute, doesn't matter, because they are going to cancel, because top at the numerator there is a distance, and in the denominator also there is a distance. Okay, so now can someone tell me what is the deformation at point P? Please solve this.
So 7.5 into 10 to the power minus 7.
7.5 into 10 to the power minus 7 meters. Okay, so like this, what you can do is you can have the deformation at any point. So all you have to do is just substitute the values in the shape functions. Okay, and you just multiply with the known values of displacement, and you can have this one. Okay, so ideally what should happen, like as you are moving away from the support, so let us say this is my beam over here or bar over here, and if I move away from the support, so what I am going to get is this type of a variation. Okay, so here you will get the maximum variation. Okay, so this variation is this value will be something like 2.5 into 10 to the power minus 6. This will be meters, this will be at node number 2, and this will be at node number 1. So even if you use a simple triangle mechanism, then also you can get this value. Okay, which is at a distance of 150. So you can also get this value as 7.5 into 10 to the power minus 7 meters. Okay, why? Because the deformation pattern or the deformation behavior from one node to the another node, it is assumed as linear. Okay, remember when we have derived the equation of when we have derived the stiffness equation or the stiffness matrix of 1D bar element, we have started with the expression something like U is equal to A1 plus A2x. Okay, so this is the variation which we have assumed. Okay, so you can see its power is basically 1. Okay, so power is 1 means what? There is a straight line variation. So this is what we have assumed, and accordingly we are getting the deformation behavior. Okay, I hope this is understood to everybody. Is there any questions, please? Okay, shall I continue ahead?
Yes, sir.
Yes, sir.
All right. So now so we have already calculated the deformation. So with this you can get the deformation at any other point. Okay, now let us quickly calculate the strains. Okay, so if you want to calculate the strain, so remember what we have done in the previous class, that strain can be calculated as strain displacement matrix, which is generally denoted by B multiplied by U. Okay, so this is nothing but your strain. Okay, and this is what your displacement. Okay, so this particular matrix becomes strain displacement matrix. Okay, so in the previous class we have also derived this strain displacement matrix. So let me quickly go back to the previous class notes. So remember here this B value. Okay, so B value was coming out to be minus 1 upon L and 1 upon L. So just refer this expression. Okay, so same expression I'm going to write down over here. So my strain value, so this strain value, okay, can be written as minus 1 upon L multiplied by the displacement at node 1 and a displacement at node 2. Okay, now remember the length is 500 millimeters in the given in the problem. So since we have to use the same units over here, so I'm going to put minus 1 upon L. Okay, so L I'm going to put 0.5 because I'm using the meters unit. So this will be 1 upon 0.5. Okay, multiplied by the deformation. So at node 1 the deformation is 0, and at node 2 the deformation value is something like 2.5 into 10 to the power minus 6. Okay, so everything is in meters. So now can somebody tell me how much is the strain in the bar?
No, 5 into 10 to the power 6.
Sorry, 5
5.
into
10 to the power 6 minus 6.
minus 6. And what will be the unit?
Unitless.
Unitless, but generally we write meter per meter. Okay, so ideally it should don't it should not have unit, but if you want you can have the units in centimeter per meter or millimeter per meter. That way also you can do it. Okay, but ideally the strain doesn't have any unit. Okay, so now what is this strain? So this strain is at which point? Okay, because you see in the earlier case we could able to find out the variation of displacement. So as your x is changing, your deformation is also changing. But here if you see this expression, so in this expression the x component is not at all there. So if you want to find out what is the strain at a distance of 150 millimeter, okay, so there is no provision because x is not at all there. So this means what? The strain is constant throughout the length of the element. Okay, so strain will always remain constant whether whether you are considering any point in the middle, or maybe at a distance of 150 mm, or maybe at some other point. So your strain will be always constant. Okay, then secondly, if you want to calculate the stress, okay, so your stress, okay, so your stress, so in the stress vector you have only x component because it's a simple bar problem. So stress can be calculated as the D matrix, okay, multiplied by your strain matrix. Okay, so here sigma x is nothing but your stress. Okay, and this is nothing but your strain, and this matrix is called as stress strain matrix. Okay, it is also called as constitutive matrix. Okay, so you can call it both. Now since this is a 1D problem, so for 1D problem your D matrix is nothing but simple E value, that is the modulus of elasticity. Okay, so finally your sigma x, okay, so sigma x now can be calculated as, this is simple E value, okay, and multiplied by the strain value. So you know we have already found out the strain is constant, isn't it? So since strain is constant, so we can simply multiply the values over here. So the value of E is given to you at the top of the problem. We can see 200 into 9 newtons per millimeter, newtons per meter square. Okay, so the same value I'm going to write down over here. So this is 200 into 10 to the power 9, and if you multiply it with strain, so your strain is 5 into 10 to the power minus 6. Okay, so can someone tell me how much is the sigma value, sigma stress? Yes, somebody please.
So 1 into 10 to the power 6.
1 into 10 to the power 6. And what will be the unit? Newtons per meter square. Okay, are you sure 1 into 10 to the power 6 आ रहा है?
Yes, sir.
कैसे आ रहा भाई? अच्छा, okay, multiplied by 5 है. Okay, fine, that's perfectly fine. So this is how you can have the variation of the stress also. Okay, and you can see the stress is constant. There is no term of x in the calculation of stress. So all you are going to get the constant stress across the length of the bar. Okay, have you understood this, everybody? Are there any questions? Yes, students, are there any questions? Okay, I'm guessing there are no questions now. Okay, so let me take another problem for you. So let me draw a simple line just to have the end of the section. Okay, so now in the another problem, now I'm taking a simple problem which was asked in some of the regular exam, so that will help you in understanding the process. Okay, so this is a uh, 2 bar kind of a system. Okay, so let me create supports for this. So we have a fixed supports over here, and we also have a fixed support over here. Okay, so there are supports like this. Here in this problem, what is given to you is first thing is the distances. Let me draw the distances for you. Okay, and here also we have a distance. Okay, so the distances which are given over here, this is 150 millimeters and this is 100 millimeters. Okay, the area of this section is given you in terms of 2a, and area of this section is given in terms of a only. Okay, so the value of E are also given. So E value is 200 GPa. Okay, and the A value, okay, so simple A value is given to you. So this is 5000 millimeter to the power 2. Okay, so this particular section is having 5000 and the other one is will be having double area of that. Okay, so in this case a load is also acting at the center. Okay, so here the load is acting and the magnitude of this load is given to you as 3000 newtons. Okay, so now we have to solve this problem. Okay, I hope the problem is clear to everybody, right? So now if you
Can
want
you
to,
please dictate the question, which what kind of question or would be asked, or what will be the pattern of the question?
so the figure will be given, values will be given, and you will be asked just solve the problem and find out the deformation at certain point, or what is the stress at certain point. Okay,
Okay. Yes.
fine. So now the very first process which is there in the finite element method is the discretization part. Okay, so let me write down over here step 1. I am intentionally covering all the possible solutions so that in the examination you should be able to get the everything. Okay, so now since this is a problem which is having two different areas, okay, so we cannot use a single element over here, but however we can use two different elements. Okay, let me use a black. So we can use one element for this part. Okay, and another element for the other part. Okay, so we can have this. Okay, so let me draw nodes now. So this is node number 1. Okay, this will be your node number 2, and this will be your node number 3. Okay, so this is what we call it as a discretization. Okay, and then if you want you can give the numbering to the elements also. So this is element number 1 and this is your element number 2. Okay, remember I am giving intentionally Roman numbers to the member numbers, okay, or the elements, and the numerical numbers 1 2 3 uh, uh, for the elements or for the nodes. Okay, not for the elements, for the nodes. Okay, so now this is the first step, and in the second step what we have to do is we have to find out the elemental characteristics, right? So step 2 is characteristics. Okay, so elemental characteristics we have already found out. Okay, it's a simple derivation over there. So I'm just directly write down over here the value of k elemental will be a e upon l multiplied by 1 minus 1 minus 1 and 1. Okay, so this completes the second step. Okay, Now the third step is what? क्या था third step? Stiffness matrix. Okay. So now there are two different elements. Okay. So element number 1 and element number 2. So now we have to generate two different stiffness matrix. Okay. So for this purpose, let me. We have already found out the value of stiffness matrix using the derivations of earlier one. So here I am going to write K1. Okay. So here K1 will be area of one element, modulus of elasticity of one element, length of one element multiplied by 1 minus 1 minus 1 and 1. Okay. Similarly, your K2. Okay. So K2 will be A2 E2 divided by L2 into 1 minus 1 minus 1 and 1, right? So now all we have to do is substitute the appropriate values over here. So your K1 will be, okay, what is your A1? So if you refer the problem, your A1 is twice A, and twice A is nothing but your 500 millimeter to the power 4. So let me write down everything in the meters. So I think it is 5 into 10 raised to power minus 3 meter square. Is it correct? Somebody?
Yes, sir.
Okay. And here you have this is 200, okay, into 10 raised to power 9. This will be in newtons per meter square. Okay. So we are keeping again everything is in newtons and meters, right? So so your A is 5 into 10 to the power 3. So your 2A, okay, so here let me write down 2A, that is the twice of the area. So this will be 10 into 10 to the power minus 3 meter to the power 2. Okay, so here I'm going to write the same value over here. So 10 into 10 to the power minus 3. Am I right? Yeah, 10 into 10 to the power minus 3. And as far as E value is concerned, so E value is 200 into 10 to the power 9. Okay, so this is into 200 into 10 to the power 9. Okay, now L1, that is the length of the first element. So length of the first element is 150 mm. Okay, so in place of 150 mm, now I am going to write 0.15 meters. Okay, so this is 1 minus 1 minus 1 and 1. Okay, so can someone tell me what is K1, the constant which is there outside the brackets?
Sir, 1.3 into 10 to the power 10.
Okay, so 10 to 1.3, that's it, or उसके बाद और भी कोई
Sir,
digits?
1.3333.
अच्छा, 1.333. Okay, so let me write down that. Okay, because try to maintain the digits, otherwise your values will be something different. Okay, 1.333. Okay, 1 minus 1 minus 1 and 1, right? Now can you directly tell me the value of K2, someone? Okay, so K2 can be calculated. So this will be A2. Okay, so area of the second element, if I remember, this is 5 into 10 to the power minus 3. Okay, into this will be 200 into 10 to the power 9. L2 is 0.1 because the length of the the second element is only 100 mm. Okay, and this will be multiplied with 1 minus 1 minus 1 and 1. So can someone tell me what is the value of K2 constant over here?
Sir, 1 into 10 to the power 10.
1 into 10 to the power 10. Okay, that's very nice. 1 minus 1 minus 1 and 1. Okay, so we have successfully calculated the value of stiffness matrix. Okay, then we have to go for the assembly. Step 4. Right? So we have to assemble the global stiffness matrix, right? So I hope you remember the assembly of global stiffness matrix. याद है? Okay, so just to have a quick recap, so if you see the element number 1, okay, so element number 1 has got starting node as node number 1 and the ending node as node number 2, isn't it? So the same numbers I am going to write down over here also. If you refer the second element, your starting node is node number 2 and the ending node is node number 3. So this I am going to write down same thing over here. Okay, so all we have to do is just create a big matrix. So this will be a 3 by 3 matrix. Okay, so your global stiffness matrix will be K global. Okay, it will be something like 3 by 3 matrix. So let me draw 3 lines over here. Okay, so this will be there, and there are 3 sections over here. Okay, and if I rewrite the same thing, so this will be column number 1, column number 2, column number 3. This will be 1, 2 and 3. Okay, so you see in both the matrices, this 10 to the power 10 is common. Okay, so I'm just going to write down this 10 to the power 10. Okay, this will be outside. Okay, so now if you refer this particular expression, so this part, okay, so this one, this is 1 it will be 1 multiplied by this constant, so this will come somewhere over here. So this is 1.333. okay, the second one, this one will also come over here, so this is minus 1.3333. so this element is the first row and the second column. So first row and second column will be also minus 1.333, and this is the second row and second column, so this will be plus 1.333. okay, so the same thing I am writing over here, but now if you refer the K2, so this will be the second row and second column. Okay, so second row and second column, and outside there is only 1. Okay, so this will be plus 1. Okay, and inside also here it will be minus 1, here it will be also minus 1, here it will be plus 1, and since there is no element between 1 and 3, so this will be 0. So finally your K global will look like this. So this is 10 to the power 10. Okay, and then this will be something like 1.333. okay, this will be minus 1.333, this will be 0, this will be minus 1.333, and here this will be 1.333 plus 1. So here it will be something like 2.333. This will be minus 1, this will be 0, this will be minus 1, and this will be only 1. So this gives me a global stiffness matrix. Okay, I hope everybody understood this. समझ में आया? Is there any questions? Okay, so this you have done multiple times, isn't it? At the same time, we have to generate the global force vectors also. So your force global. Okay, so this is a vector over here. Okay, so if you refer the problem, there is no load at node number 1, there is no load at node number 3, there is only load which is there at node number 2, and that too in the direction of the x-axis which we have assumed. So this will be 3000 newtons. Okay, so your simple global force vector will be here, it will be 0, here it will be 3000, of course this will be plus, and this will be 0. Okay, so this your global force vector is now ready. Now in the fifth step, we just have to solve the stiffness equation. Solve the stiffness equation, right? So your stiffness equation is basically a simple expression. So this is K global into U global equals to, we have force global. Okay, so I'm just writing down the same matrix one more time over here, that is K global. So your K global is something like 10 into 10 to the power 10. Okay, this is 1.333, this is minus 1.333, this is 0, this is minus 1.333, this is 2.333, this is minus 1, this will be 0, this will be minus 1, this will be plus 1. Okay, multiplied by, you have the global deformation at node 1, global deformation at node 2, and global deformation at node 3 equals to, Your force vector will be, this will be 0, this will be 0, and this will be, I think this is 3000. Okay, so our global stiffness equation is now ready. And as you know, if you refer the problem, the deformation at node 1 and the deformation at node 3, it is 0. Why? Because there is a fixed support over here. So there is no point, that this point is not going anywhere. So all we can have that this value, u1 value is 0 and u3 value is also 0. So now since this is 0, we can go for the reduction of the stiffness matrix by eliminating the corresponding rows and corresponding columns. So since u1 is 0, so I have to eliminate the first row, okay, and the first column. Now since u3 is 0, so I have to eliminate the third row. So it is u3, so third row, and at the same time we have to eliminate the third column. Okay, so now if this is the case, our global stiffness matrix now can be reduced to a simple matrix. So this will be 10 into 10 to the power 10 multiplied by 2.333, okay, and this will be multiplied by u2, okay, equals to, we have this as 3000 millimeters, okay, no, 3000 newtons. Okay, so now can you solve this and give me the value of u3, sorry, u2 please. u2 कितना आ रहा है?
128.589 into 10 raised to power minus
128.589 into 10 raised to power minus 9. Units will be meters. Is it okay?
Yes, sir.
Okay, so you see the deformation value is very, very small, right? So this solves the FEM problem. Now what comes? The post processing. Okay, so in the examination you may be asked what is the deformation and what are the stresses. Okay, so let me go for step 6, that is extra calculations. Okay, so in the extra calculations there are many questions. Okay, so for example, if in the examination, if it is asked what is the deformation at a distance of 100 millimeter, okay, so 100 millimeter, okay, so I'm just writing that what is the u value, okay, when x equals to 100. Okay, so this is my question, right? So now if this is my question, in that case, if you refer the problem, so in the problem itself you will find that this was a fixed support over here, okay, and the total distance from this end to this end, I'm talking about only first element, so this distance was something like 150 millimeters. Okay, so your section of this 100 millimeter will come somewhere over here, isn't it? So that this distance will be 100 millimeters, isn't it? So this is 100 millimeters. So basically what I'm trying to say over here is the point 100 millimeter comes under the element number 1. This is what? Element number 1. Okay, so we have to refer to the element number 1 only. So now if you want to calculate the displacement, you have to refer to the displacement equation. So your displacement equation was u is equals to n1 n2 multiplied by, this is u1 and u2. Okay, so this is for element. Okay, so here the value of n1 is nothing but what? 1 minus x by l, this is x by l multiplied by, now this will be your u1, so this is your node number 1. Okay, so this is node number 1 and this will be your node number 2. So here you will have the first node, that is u1, and here you will have u2. Okay, so all we have to do is just substitute the value of x as 100, here also as 100, the length value. So now here the length of first element has to be given, okay, not the entire length, okay, because we are talking about first element only. So here the length will be 150 millimeters and here also this will be 150 millimeters. As far as U1 is concerned, U1 is 0 because there is a fixed support over here, and your U2 is something like 128.589 into 10 to the power minus 9. Okay, so this is going to give you the deformation value at point number point. Let us say this is point is P. Okay, so the P point which is located at a distance of 100 millimeters from the left support. So can somebody tell me the value, please? Deformation at U, deformation U value, please. Yes, students.
85.726 into 10 raised to power minus 9.
Somebody please check.
Yes, sir.
ठीक है?
Yes, sir.
So in this way you can have the deformation at a given point. Okay, now again let me I just want to find out what will be the deformation. Let us say I want to know what is the deformation. What is the deformation when x equals to 200? Okay, so let me draw the problem one more time. Okay, so this was my problem. It was like this. Okay, and then the problem was like this. Okay, it was like this. Okay, and if you remember, this distance was 150 mm. Okay, and the other distance, that is the distance at the other end, this distance is I think 100 mm. Okay, and this was your origin, right? And this was your x-axis, right? So now I want to have what is the deformation at a point which is located at 200 millimeters, right? So if I locate this 200 millimeter, so your 200 millimeters is somewhere over here. Okay, so if I draw a straight line, if I draw a dimension over here, so this distance is basically you have 200 millimeters. Okay, so now you see our point. Let us say this is point number Q, for example. Okay, so this is your point number Q. So this Q point comes under the second element now. Okay, so if you want to find out the displacement at point Q, you have to refer to the second element now. So the expression will remain same. So this will be U equals to, this will be N1, this will be N2. Okay, multiplied by, you have U1 and U2. So this was at the elemental level. Okay, now if you go for the global level, what is going to happen over here? So here we will be having N1. Okay, here you will be having N2, but at the global level, the first node of the second element. Okay, so this is your second element, isn't it? So second element का जो पहला node है, this is the first node. So this node is nothing but second node. So this should be U2, and the second node of the second element is node number 3. So this will be U3. Okay, everybody understood this? समझ में आया ये?
Yes, sir.
Yes, students, is it okay? Okay, fine. So now let me go for the U now. So N1 expression will remain same, that is 1 minus x by L. This will be x by L. Okay, and multiplied by, you have U2 and U3. Okay, now again I am dealing with the elemental level only. Okay, so if you refer the distances, so here the distances has to be measured. So if you refer only this element, that is second element, so this distance, okay, ये distance कितना आएगा? 50 mm. Okay, so I am talking about element part only. So your x over here, this will be now 50 mm, this will be also 50 mm, and length. So I am talking about second element, so your second element length is 100 mm. Okay, and U2 value, I think U2 value you have already calculated, as this is 128, something like 128.589 into 10 to the power minus 3, whereas your U3 value is 0 because there is a fixed support over here. Okay, so now can somebody tell me what is the displacement at point Q?
Sir, 1.
बताओ।
Sir, 1.
1, आर यू श्योर? मेरे हिसाब से इसका आधा आना चाहिए। 128.589 इंटू 10⁻⁻⁹ उसका ठीक आधा आना चाहिए। Yes, students, please do the calculations.
6.43. So
Sorry?
6.43 into 10⁻⁸.
हाँ, यानी exactly इसका आधा है ना?
Yes, sir.
Yes, sir.
Okay, how much is the value? 6 point?
6.429.
429.
64.29 into 10⁻⁻⁹.
हाँ, वो एक ही बात है।
Simple.
ओके, इंटू यहाँ पे आएगा तुम्हारा 10⁻⁻10 आएगा शायद।
-8.
So -8.
-8. Okay. Okay, so this will be -8. This will be meters. Okay, so now you have to just understand that whenever you are finding out the displacement at any point, you have to refer to that respective element. ठीक है, वो point जिस element में है, you have to take the characteristics of that particular element only. Okay, don't take other element, otherwise you will be in trouble. Okay, so this is how the deformation can be calculated at any point in the finite element method problem. Okay, now let us talk about the stress. So in case if you have been asked what is the stress at the node number 1, or maybe what is the stress at the element number 1. Okay, so I'll just tell you how to calculate the stresses and strain. Let me calculate the strain first. So generally you calculate the strain as your strain displacement matrix into U matrix. Okay, so this is B, okay, this is U, and this is your strain. So this is a generalized expression. So if you want to calculate the strain at the first element, okay, so here I'm going to write down over here. So let us say this is element 1. Okay, I think I have made a mistake in element over here, and let me write down over here, this is element 2. Okay, so we will calculate the strains at element 1 as well as element number 2. So if you want to calculate strain at element number 1, so this will be strain at element number 1. Okay, this will be the B matrix. Okay, so strain displacement matrix at element number 1, and here you have the U term. Okay, so your U is basically for element number 1, it is U1 and U2, because the first node at element number 1 is U1, 1, and the second node is 2. As far as the strain in second element is concerned, okay, so this will be the value of B2, that is the strain displacement matrix at the second node. And for the second element, the first node is second node and the second node is your third node. Okay, so you will have to substitute the values accordingly, right? And what is your generalized expression for B? So B is something like 1 upon L, minus 1 upon L and 1 upon L. So here I can write the same term over here. So this is minus 1 upon L. So I'm writing down L1 over here because I'm right now dealing with element number 1. So this will be plus 1 upon L1, okay, multiplied by, you have U1 and U2. So this is going to give you the strain in the first element. Similarly, the strain in the second element can be calculated as 1 upon, here this time it will be L2 because I am dealing with the second element now. So this will be minus, this will be L2, okay, multiplied by, now you have U2 and U3. Okay, now remember, we know that displacement at node 1 is 0 because there is a fixed support, and the displacement at node number 3 is also 0 because there is a fixed support. And I have you also know that the value of U2, that is the deformation at the second node, is something like 128.589 into 10⁻⁻⁹. Okay, so here also you just have to write down 128.589 into 10⁻⁹. Okay, and if you remember the L1 and L2 values, okay, so your length 1, so length 1, I think the L1 value is 150 mm, so I'm writing down 0.15, so L1 will be also 0.15, whereas your L2 value is 100 mm, so I'm going to write 0.1. Here also I'm going to write 0.1 over here. Okay, so if you solve this, you should be able to get what is the element strain in the in the element number 1, and what is the strain in the element number 2. Okay, so can someone tell me the values, please? Batao. Come on, students, hurry up.
So 857.26 into 10 raised to power minus 9.
Yeah, this
1.
is strain in first element.
Yes.
Okay, so let me write down. So this is 857.2
0.26
into 10 raised to power
minus 9.
minus 9. Okay, meter per meter, right? And what about the other one, strain? Yes,
So 1285 point.
Minus 1285.
yes,
0.89 into 10 raised to power minus 9.
1285
0.89
into 10 raised to power minus 9, correct?
Yes. Yes, sir.
Meters per meter,
Meters.
right? So you can calculate the strains in either this part or that part. Okay, now if you want to calculate the stress, okay, so stress calculation is very easy. So stress can be calculated as a simple D matrix into your strain matrix. Now in case of 1D problem, this D is nothing but your modulus of elasticity, and the modulus of elasticity is given to you in the numerical as 200 GPa. So that is 200 into 10 to the power 9. This will be newtons per millimeter square. Okay, so your sigma 1 is nothing but E into strain 1, and your sigma 2 is nothing but E into strain 2. So in this case, in this problem, the value of E is constant. So here the modulus of elasticity for this problem is same, and here it is same. So if they are different in that particular case, in this expression you have to use the value of E1 over here and E2 over here. So for example, one is made up of copper and one is made up of, say, steel. So accordingly you have to choose the modulus of elasticity. Okay, so correspondingly now we can get the value of sigma 1, that is the stress in the first element, as 200 into 10 to the power 9 multiplied by the strain which we have calculated, that is 857.2 into 10 to the power 9 negative. Okay, so give me the values of sigma 1 now.
171452.
1714.52.
171452. Yes, sir.
So this will be newtons per meter square. Somebody please cross check this. And at the same time you can calculate what is the strain or what is the stress in the second element. Yes, somebody please tell me what is the stress in second element.
Correct,
Minus
sir.
257178.
Correct? Eh?
Yes, sir.
Yes.
Okay, great. So you need to understand this value is positive. Okay, sigma 1 is positive and sigma 2 is negative. Okay, so one is creating compression and one is creating tension. Okay, so now if you see the problem here, so you can see the load is acting at the center point, isn't it? So since it is acting at the center point, what you should get on the first side, that is on the first side you should get tension, and on the other side you should get the compression. So always remember this, that the positive value, okay, so here this is nothing but your tension. Okay, why? Because this is positive, and here since it is negative, so this stands for compression. Okay, so this is how the numerical is solved using the finite element method. Okay, I hope you have understood this. Are there any questions? Okay, so we will take a last problem. Okay,
सर स्ट्रेस स्ट्रेन डायग्राम्स
इसमें देखो स्ट्रेस तो कांस्टेंट ही है ना, स्ट्रेन इज कांस्टेंट, स्ट्रेस इज कांस्टेंट, and if you want to plot the deformation diagram, okay, so deformation diagram, it is very easy because the deformation is quite straight, because your equation is something like this one, isn't it? That is something like u is equal to a plus b times x, ये ऐसा कुछ लिया था हमने, बराबर है? So since this is the case, so what you can do is you can use this particular expression. कौन सा वाला? ये वाला. Okay, and you can use this particular expression to find out what is the deformation at the intermediate point. तो यहाँ पर देखो हमने p पे निकाला है, तुम यहाँ पर भी निकाल सकते हो बीच बीच के, and then you can plot a variation, and I am sure you are going to get a variation something like this. Okay, because you see at the center part you will be getting the maximum deformation. Okay,
सर यहाँ पे नॉन सिमेट्रिकल रहेगा ना,
sorry,
यहाँ पे नॉन सिमेट्रिकल रहेगा ना ट्रायंगल,
नॉन सिमेट्रिकल रहेगा एक्चुअली, इसका लेंथ ये साइड में कम रहेगा,
हाँ हाँ,
बस बाकी कुछ नहीं,
राइट साइड इंक्लाइंड रहेगा,
राइट साइड में कम रहेगा, बट द वैल्यू विल बी सेम. सो इफ आई ड्रॉ दिस इट विल लुक लाइक दिस. Okay, let me draw this for you. So it will look like this. So we have, so this will be 150. Okay, and here ये तुम्हारा आएगा कुछ इतना, पीक पे आएगा यहाँ पर. Okay, and you will get a straight line like this. Okay, and then you will get a straight line like this. Okay, and this will be the maximum value. So this maximum value is nothing but 128.589 into 10 to the power minus 9. Okay, यहाँ पर तो तुम्हारा already 0 है, isn't it? Okay, so in this way you will get the variation of the deformation. As far as strains and stresses are concerned, they are quite simple, because the strains, one is positive and one is negative, isn't it? So here if you draw a strain diagram, for example, तो strain diagram तुम्हारा कुछ ऐसा बनेगा. Okay, so you will have a positive strain. Okay, so positive strain means it is a tension. Okay, then it will suddenly go over here, and then you have a compression strain. It will be like this. So this will be tension and this will be compression. Okay, so values over here, so this value is nothing but this value, and this value is nothing but a value which is over here. Okay, and it is constant. A similar type of figure you will also get in the stress also. Okay, so you have a straight line which is like this. Okay, and you will have a positive strain at the top. Okay, for a distance of 150, and after that you have a negative stress. Okay, so this value will go over here and this value will go over here. Okay, so indicating this is a tension and this is a compression. I hope this is clear to everybody.
yes sir.
Okay, so let us quickly take one more problem. Okay, then we will stop. Okay, fine. So here I'm going to take a different problem now. So let me draw the figure for you. So we have a bar. Okay, it is something like this. Okay, students, I got disconnected. Okay, can somebody please confirm, are you getting my screen or not?
Yes, sir.
Okay, so basically what I was trying to tell you over here is the area is not constant, area is continuously reducing. Okay, and in the problem the area is given in terms of the function of length. Okay, so as the area is changing or the length is changing or the x value is changing, your area is also changing. So the expression is given to you as a0 into e to the power minus x upon 2 times L. Okay, so this is the equation for the area. Now on this problem, in this problem there is a joint over here and the load is acting like this and its value is P. Okay, and we are assuming the x-axis also in the same direction like this. Okay, so in place of drawing the horizontal figure, I am drawing the vertical figure. Right, now you see when we have gone for the derivation of the stiffness matrix, we have assumed that the area is constant within the element. Okay, so area is not at all reducing or increasing, it is constant from node number 1 to node number 2. But as far as this problem is concerned, this is not the case, isn't it? In this case the area is continuously changing. Now how to do this? Okay, how to solve this? So the very first thing which we need to understand over here is the discretization. So in the first step, we have to just go for the discretization. So now I am going to discretize this problem using only two elements. Okay, so here I'm just using, this is the discretized structure, you can say. So this will be node number 1, this will be node number 2, this will be node number 3, so that this will be my element number 1. Okay, and this will be my element number 2. Okay, but now you see the area is not at all constant. So how to handle this particular problem? So what I'm going to do is I'm going to take three sections. Okay, one is the section over here. Okay, the second is the section over here, and third is the section over here. Okay, so here the length is I have not mentioned the length. So the length of this problem, okay, so the total length of this problem is given to you as 2 times L. Everything is there in terms of L. Okay, so here I am assuming the distance between here and this section. Okay, so this I am assuming this as L. Okay, so all I have to do is here the x value will be 0, here x value will be L, and here x value will be twice L. So the same thing I'm going to substitute in this expression. So this is A when x equals to 0, this will be A when x equals to L, and this will be A when x equals to 2 times L. So all we have to do is this will be A0 into E to the power minus, so this will be 0 divided by twice L, and here this will be A0 equals to E to the power minus, this will be L divided by 2L, and this will be something like A0 into E. Here this will be minus, this will be 2L divided by 2L. Okay, so this A0, so let me use some different color now. So your A0, okay, so A0 कितना आ रहा है? A at 0 कितना आ रहा है? I think this will be simply A0. बराबर है? Yes, somebody please respond.
Yes, sir.
Yes, sir.
ठीक है. What about A at L?
0.60.
0.6065 times A0.
A0.
Okay, and here A times 2L is coming out to be
3678.
0.3678 times A0. बराबर है? Okay, are you getting these values? बराबर है?
Yes, sir.
Yes, sir.
Yes, sir.
So now, see, as per the basic assumption, the area should remain constant within the element. Okay, but right now you see here we have different area, and at this location we have different area. So what we are going to take is the average of these two area. Okay, so if you take the average of these two areas, so this is A0 plus 0.0656 times A0 whole divided by 2. So your average area of this element is coming out to be something like कितना आ रहा है average?
Sir, 0.8032.
Yes, 0.803 times A0. So this is a average area. Okay, and again if you take if you take the average of these two area and if you provide it over here, so how much is the average area of these two? Is it okay?
Yes,
आ रहा है?
sir.
चेक करो. I am getting 0.487 times A0.
Yes, sir.
Okay, so now I am going to draw one figure in front of you. You can just refer this. So just a moment please. सर 10 मिनट में आ रहा हूँ, क्लास चल रहा है. सर 10 मिनट में आ रहा हूँ, क्लास शुरू है. हेलो सर 10 मिनट में आ रहा हूँ, मेरी बात खत्म हो गई. Yes, students, are you here? All right. So you see, our problem was initially like this. Okay, where the area was continuously reducing, and what I have done, I have modified the problem which is looking something like this. So here the area was reducing, but here if you see, the problem is defined or redefined as a bar which is having this shape. So here this will be 0.803 times A0, this will be the area, and this will be 0.487 times A0, and the distances will be something like here, this will be L. Okay, and here also from here to here this is L. Okay, and then this is fixed over here, it is something like this. Okay, and then we have a load which is acting at the bottom, so this is nothing but your p value. Okay, so I have just redefined the problem, and then now I'll be in a position to solve this particular problem. Okay, now if you solve this, so I hope everybody will be in a position to solve this, isn't it? Because it's a simple thing now. So generally what we do is the K. So K is nothing but A E upon L into 1 minus 1 minus 1 1. So here I have divided this into two parts. So your K1, Okay, so K1 will be something like A1, E will be constant, L will be L only. Okay, this will be 1, minus 1 and 1, where this A1 value is nothing but the average value, isn't it, which is something like 0.803 times A0, right? Similarly, the K2 value will be something like A2 into E divided by L, 1 minus 1 minus 1 1, where this A2 value will be something like 0.487 times A0. Okay, so now we can assemble the global stiffness matrix, right? So we can have the K global. So I am directly writing down the K global values. It is there with me. So I can take out A0 E upon L outside. Okay, and then I can have this as 0.803. This will be minus 0.803. This will be also minus 0.803, and here you will be getting something like 1.29, and here this is minus 0.487, minus 0.487, and here also 0.487. This will be 0 and this will be 0. So this is how you are going to get the global matrix. And if you refer the force global matrix, so this will be the first node will be 0, second node will be 0, and third node will be subjected to P. Because if you see this particular figure, here there is no load, there is node, only at this point there is a load over here, right? So if you solve this, so our stiffness equation is nothing but K global multiplied by U equals to force global. Okay, so now if you solve this, so what you are going to get, you will get something like A0 E upon L. Okay, so here you will have some values, here you will have some values. Okay, so I am not writing down the values, they are already there in front of you. Okay, and here you will be having the global displacement at point 1, at point 2, and at point 3, and here you will be having this is 0 0 and this is P. Okay, and what we know is that the displacement at point 1 is 0. So what we can do is we can eliminate the first row and we can eliminate the second row. Okay, so if you rewrite this particular expression, so what you are going to get is A0 E upon L into, here you will be getting something like 1.29 minus 0.487 minus 0.487, and this will be 0.487. Okay, multiplied by, you will be getting something like U2 U3, okay, equals to, this will be 0 and P, right? So this is how this will be a 2 by 2 expression now, and if you solve this, you should be in a position to get the values of the unknown displacements. Okay, so if you solve this, so you are going to get the value of U2 and U3 as, your U2 comes out to be 1.2453 PL upon A0 E, and your U3 comes out to be 3.2986 PL upon A0 E. Okay, so now since your unknown equations are there, you can find out whatever, you can calculate the stresses and you can calculate the strains using this particular expression. Okay, I hope you have understood this. Are there any questions? Yes, students, are there any questions, please? Shall I continue?
Yes, sir.
Okay, the last part which I wanted to tell you over here is like this. So see what we have done in this problem. What we have done in this problem is this one. Okay, so I have a problem which was like this. Okay, I have converted this problem into this. Okay, so you see there is a great difference between the actual problem and what we have assumed. And because of this, what is going to happen is the solution whatever you are getting is it will not be accurate one. So for example, I am targeting this displacement, that is displacement at the point of application of the load. So here if I draw a graph, for example, if I draw a graph, so here I have used how many elements? Here I have used only 2 elements. Okay, I have used 2 elements, and here I am just putting the displacement at point of application of load. Okay, so here if I draw this value, so when I am using just 2 nodes, I am getting a value which is something like this. Okay, I can solve the same problem using 3 elements like this. We can solve this, isn't it? Okay, so if I use 3 elements, I'll be getting a deformation somewhere like this. Okay, so if you use the n number of elements, okay, so for example, if you use n number of elements, so what we will get? So here you will get a 1 element over here, 1 element over here, 1 element over here. So if you discretize this with n number of elements or a more number of elements, so what you will find that this particular problem, okay, so this original problem is matching very good as far as more number of elements are concerned. Okay, it is not matching over here, it is not matching over here. Okay, because this is very poor assumption. But if you use smaller elements, very small elements, so it will match with the actual problem. So here if you use, let us say, n number of elements over here, so you may be getting a value something like this. Okay, so if you draw a curve of this displacement, so you will get a displacement curve which is something like this. So as you increase the number of elements, what you will find, there is a great variation in the displacement, but this displacement will be there, or the variation of the displacement will be there up to certain number of elements. Okay, let us say, for example, up to, let us say, 50 elements, for example. Okay, so after 50 number of elements, what you will find, if you use 51 elements, okay, or if you use even 90 elements, or even if you use 100 elements, what you are going to get is the value which is coming over here, the same value will come over here, and basically after certain points this curve is going to become constant. Okay, so we have to solve a problem with number of elements which are giving you the same results. Okay, so if you are solving the problem using, let us say, 10 elements, for example, so your solution will not be correct. So if you are using a number of elements beyond this particular point, then your solution will be correct one. Okay, so this is this particular portion is called as convergence. Okay, so you have to ensure that whenever you are using the finite element method to solve any kind of problem, make sure that your problem is getting solved with more number of elements. More the elements, more will be the calculations, but the accuracy will be higher. Okay, but practically it is not possible to solve this problem, let us say, using 50 elements. Okay, because your matrices will be 50 by 50 global stiffness matrix will be size. So it is really not possible. That's why we are using a software for solving this problem. Okay, so with the software you can have thousands of elements and then you can get the correct solution. Okay, I hope this funda is clear to everybody. Yes, students, is it clear to everybody?
Yes, sir.
ठीक है then. Okay, so we will stop now. Let me stop the recording. Okay, are there any questions?